Welcome to Elementary Calculus, Chapter 4, Section 3. We're in a chapter where we're talking about finding derivatives. And in the first section, we looked at some of the processes for taking derivatives of constant values and a variable being raised to a power and a variable being raised to a power where there's a coefficient involved. And in the second section, we looked at the product rule and the quotient rule. And now we're going to look at another set of circumstances which is going to require a different tool, and this one is called the chain rule. And the chain rule is used when we have a composition of functions like f of g of x, and the first example gives us two functions, f and g, and asks us to build the composition function and then evaluate it given an x value of -3. And I think we'll go so far as to build the composition function anyway. So our function f of g of x is equal to, now remember we're taking the g function and we're plugging it into the function f, which means that this x and this x and this x are going to get replaced by g of x. So now we have 8 times g of x squared minus 5 times g of x. And then let's replace those g of x's with what g of x actually is. So we have 8 times 7x plus 9 quantity squared minus 5 times 7x plus 9. In order to continue expanding this, we need to FOIL and combine like terms here, and then we'll distribute this multiplication by -5 to these two terms. So FOIL and distribute. The FOILing process, without actually doing the multiplication by 8, leaves us with 8 times 49 x squared plus 63x plus 63x, which means plus 126x plus 9 times 9, which is 81, minus 35x minus 45. Then you would need to distribute multiplication by 8, and then your next step after distributing, sometimes my pen doesn't work and I just get frustrated and I think if I keep writing, maybe it'll look legible. It never looks legible. After you distribute multiplication by 8, your last step will be to combine like terms, and after that you could go through the motions of plugging in an x value of -3 and evaluating f of g of -3. I'm not going to do that. You know how to distribute, you know how to combine like terms, and you know how to plug in a number. Just make sure that when you plug in a number like -3, that if you're squaring it, it should become positive. So if you're typing this into a calculator, maybe make sure to use parentheses. The next example asks us to write this function as the composition of two functions f and g. If you'll notice here, g is sort of inside of f. And in this y equals example, -6x plus 10 is inside this process of raising something to the 9th power. So we would let g of x be our inner function, and the f of x function, f provides a particular function. It takes stuff and raises it to the 9th power. What kind of stuff? whatever we put into the function. So I could definitely replace this x and this x with a g of x, and then we would be raising g of x to the 9th power. What's g of x? In this particular case, g of x is negative 6x plus 10. So if we want that to be raised to the 9th power, we have to take g of x and plug it into f of x, which would give us f of g of x. So you can see how this y equals equation, the right-hand side of it, does represent a composite function, or the composition of two functions. These two things are not automatically interchangeable, f of g of x and g of f of x. In fact, this is only the case when f and g are inverse functions, like squaring and square rooting. And now we really get to the crux of the matter, which is the chain rule, the primary subtopic and really overarching topic of this section. And the chain rule gets implemented when you're working with composite functions. So here we're taking the derivative of y with respect to x. What's y? Y is a composition function, f of g of x. How do I take the derivative of a composite function? The answer is you take the derivative of the outer function while leaving the inner function intact, and then you secondarily, or sort of after the fact, multiply by the derivative of the inner function. That's almost not helpful at all. So let's have a look at it in an example. The outer function is raising something to the 2/3 power. The inner function is x to the 3rd minus 8. So here's what y prime looks like. The outer function, which is the 2/3 power, I'm going to take this exponent and multiply it out here by this leading coefficient. In fact, let's modify this problem and let's put a 5 out here. Sort of make the example a little bit more extreme, okay? So now I have the existing coefficient times that exponent that we just multiplied out front of 2/3. And then here's the inner function. I'm not even going to look at it at the moment, but I'm going to do what I normally do with this exponent, and I'm going to subtract 1 from it. So I'm not going to do anything to this inner function. Let's just leave it as it is. X to the 3rd minus 8. Excuse me. Then we're going to perform this part of the process and multiply by the derivative of the inner function. So the inner function is x to the 3rd minus 8. So let's multiply by 3x squared minus 0 if you want. The derivative of a constant value is 0. So if that's helpful for you to have that minus 0 in there, that's fine. So the outer function involved, and now I don't love that this 5 is in red. The outer function involves multiplication by 5 and raising something to the 2/3 power. The inner function was the x to the 3rd minus 8. And then you just have to go through and clean this up. So let's go ahead and finish that process. Alright, so really I just focused on cleaning up the sort of the first half of this process. Now let's incorporate this multiplication with this multiplication, because we really have three things that are being multiplied together here. We have the 10/3, we have our inner function to the -1/3 power, and then we have the 3x squared. So I'm going to shuffle things around a little bit using the commutative property of multiplication. That says that I can multiply the first and third factors together and sort of then tack on the middle factor. So it's going to look like this. This division by 3 is going to cancel out with this multiplication by 3. The 10 is still there. This multiple of x squared is still here. I'm just going to write it second, and then the third factor that's still there is the x to the third minus 8 to the -1/3 power. We could take the x to the third minus 8 to the -1/3 power and put it in the denominator with an exponent of +1/3. We could put it in the denominator, and instead of writing it as to the 1/3 power, we could write it as the cube root of x to the third minus 8. You cannot distribute the cube rooting. You cannot take the cube root of x to the third and the cube root of 8. That is, there's no distributive property of exponenting over subtraction nor addition. So the best we could do is put it in the denominator as the cube root, or to the +1/3 power. Let's look at this as an analogy. Let's look at this. Let's compare what we just did. Let me say that a little more simply. Let's compare what we just did to a process that should be similar. Let's try y equals 5x to the 2/3 power. Let's see if this is similar at all to 5 times a whole bunch of weird stuff to the 2/3 power. What's the derivative of this equation, y prime? How do I find the derivative of this? You know how to do this. You take the exponent and multiply it by the coefficient. So the 5 is there, and you multiply that by the 2/3, and you keep the variable, and then you decrease the exponent by 1, which would give us 10/3 times, let me not write that there, I'll put it on the next line, which equals 10/3 times x to the -1/3 power. Gee, this looks very similar to this. Well, it looks similar to, maybe it looks more similar to this? Yeah, it looks more similar to this, except we don't have this times 3x squared. Why isn't that times 3x squared appearing in here? Could it or should it? If I were to continue with this problem, if I were to continue this and implement the chain rule, I would have to multiply by the derivative of this inner function, x. X is the inner function here. Let's do that. Let's multiply by the the derivative of x. What's the derivative, d over dx? What's the derivative of x? It's just 1. So really there is an invisible multiplication by 1 happening there. In the previous sections, all of the times that you were taking the derivative of x to some power, you were actually doing this. Well, you weren't really doing it, but it was happening. But because it was invisible, we didn't tell you about it yet. But you've been using the chain rule all along. It was just sort of happening as a quiet, invisible byproduct. But here, now that our inner function isn't just an x, this process of multiplying by the derivative of the inner function becomes really important. When it was just an x, the derivative was just multiplication by 1. So the fact that we've been skipping it all along didn't really matter. However, when your inner function is something other than just x, then we must tack on that extra process at the end of multiplying by the derivative of the inner function. So what I just did in this example problem, is exactly what you've been doing all along. We've just tacked on this additional part, okay? In our previous examples, this stuff was just an x, and this was just an x, which meant that this was just a 1. That's what we've changed in our progression to this third section of this chapter. Let's have a look at another example. Find all values of x for this function where the tangent line is horizontal. In other words, where the first derivative is equal to 0. And that is what I just did and said there, is I translated this, where the tangent line is horizontal. When I read that, I immediately think, oh, they want me to set the first derivative equal to 0. Is that always going to be the case? Can I always translate it that way? I hesitate to say always. But for the most part, if you're looking at a function and you have a tangent line that's horizontal, in other words, a tangent line with a slope of 0, then at that point, on your function, your first derivative should be equal to 0, because the first derivative represents the slope of the tangent line, or the rate of change of your function. And if it's 0, then it's neither increasing nor decreasing. So we should be able to take the first derivative of this function and set it equal to 0. This is going to be a little labor intensive. So make sure your pencil is sharp, and let's give it a shot. So we have a quotient, right? Our function is a fraction, which means we're going to use the quotient rule, which I like to use low d high minus high d low all over low low, or low squared. So I'm going to write this as f prime of x equals, and I know it's going to be a fraction, I've got low, which is x squared plus 1 all to the third, times the derivative of my numerator, so d high. I'm going to write that as the numerator with a prime on it, minus low d high minus high, which is x, times d low, make sure that looks like a square there, oh, I'm mixing my numbers here, sorry, x squared plus 1 to the third, and then we're going to take the derivative of that. So that's low d high minus high d low all over low squared, which is x squared plus 1 to the third squared. That's low low, or low squared. Okay, so we have embarked on finding the first derivative of f of x, and we have started out by using the quotient rule. So in your notes, you might want to include a note that says that we went from here to here by using the quotient rule. Now, what do we have to take the derivative of in here? Taking the derivative of x to the first power is going to be easy. Taking the derivative of this is going to be a different story. That's going to require the use of the chain rule, because there's an inner function and an outer function. So let's keep going. Whoa. Sometimes I set my hand down on the screen and it just takes off. Don't know why that happens. Okay, so equals. This first factor is going to stay the same. X squared plus 1 all to the third times, now the derivative of x, maybe I'll switch colors to do this, and we'll say that that's equal to 1, Great. Minus the x value from the numerator times, and now we've got another derivative coming. Here's where we're going to use the chain rule. I'm going to take the exponent, multiply it out front, and then decrease that exponent by 1, leaving my inner function the same. I'll put it all in brackets still, maybe. Brackets? No brackets. The 3 multiplies out front, parentheses, x squared plus 1, decrease the exponent by 1, so now it's a 2, and then here comes the chain rule. Now we have to multiply by the derivative of the inner function, so we will multiply by 2x, or 2x plus 0 if you wish. We've taken this inner function, taken its derivative, and there it is. Well, that wasn't so bad. When you break it up into little pieces like this, okay, that's not so bad. And then in the denominator, I'm not going to multiply this thing all the way out, not a chance. I'm going to leave it as x squared plus 1 to the power of 6. That's the power rule for exponents. When you have a thing to a power, you multiply the powers. All right, now what am I going to do? In the numerator, I've got an x squared plus 1 to the 3rd. And then in the next term, I've got an x squared plus 1 to the 2nd. And in the denominator, I've got an x squared plus 1 to the 6th. I think what we should do is, in what order do I want to do this? Let's just clean it up a little. Let's just clean it up a little first. Tidy up. So the x plus 1, or x squared plus 1 to the 3rd is still there. I don't need to include the multiplication by 1, minus. Now, if you look up here, here's a multiple of x, here's a multiple of 3, here's a multiple of 2x. I'm going to multiply all of those together. So the 3 times the 2 gives me a 6. The x times an x gives me an x squared. And then we have this statement in parentheses, the x squared plus 1 quantity squared. And our denominator stays the same. Now, how much space do I have? I've got some space. I want you to envision that x squared plus 1 is actually an m, and an m, and an m. So what we have in the numerator is we've got an m to the 3rd, and an m squared, and down here we've got an m to the 6th. I'm going to cancel out 2 multiples of m from each one of those terms. In the numerator, I've got 2 terms, and in the denominator, I've got 1 term. Numerator, term number 1. Numerator, term number 2. Denominator, there's only 1 term. So I'm going to, again, cancel two factors of x squared plus 1 from here, 2 factors of x squared plus 1 here, which leaves me with 1. I don't want to do this with a highlighter. I'm going to cancel 2 factors of x squared plus 1 here, which knocks both of those out. I'm going to cancel 2 factors of x squared plus 1 from there, leaving me with 1 still. And I'm going to cancel 2 factors of x squared plus 1 from there, which leaves me with 4 of them. And then I will rewrite. So we can call this reduce by x squared plus 1 squared. And that leaves us with still a fraction, x squared plus 1 to the first power minus 6x squared. Oh, I'm not really protecting this x squared plus 1 from anything anymore, so I don't really need to have these parentheses. And in the denominator, we still have 4 factors of x squared plus 1. In the numerator, we can combine like terms, and I think that's going to be about it. 1x squared minus 6x squared is negative 5x squared. The plus 1 is still there, and in our denominator, we still have these 4 factors of x squared plus 1. So we had to implement, again, multiple tactics here. The very first one that we used was the quotient rule. And from there, we took a regular derivative. But here, we had to use the chain rule. So if you want to put a little note on that one, chain rule. And from there, it was algebra. Really just tidying up here by multiplying some factors together. Here, reducing by a common factor from all of our terms, and then combining like terms. And that was it. So don't let these overwhelm you. Realize that you're going to have to use different tools, and as you use each tool, take it slow and consider using different colors. And if you want to be able to erase, then maybe that means getting different colored pencils and a high quality eraser so that you can still erase if need be. Otherwise, if I was doing this in pen, right, if I made a mistake, that could get pretty ugly. If I were doing this in pen, I don't know, maybe I would just put a bracket around this and cross it out instead of scribbling it out. I made a mistake. Don't do that, because you might want to look back into those brackets. Some of that stuff was still pretty good. You want to copy it down onto the next line. So don't do the scribbles. Maybe just bracket it, put an X next to it, and keep going and plan on getting it right the next time, especially as you're just practicing. If you had to hand it in to a professor, then you'd want to probably rewrite it or make sure you're using pencil all the way through. But if it's just for practice, don't hesitate to keep your mind organized by using a couple of different colors. A common error when using the chain rule is to forget to multiply by g prime. Yeah, for sure. Honestly, if you forget to multiply by g prime, then you're not really using the chain rule. You're just taking an incorrect derivative. And another common mistake is to put g prime into the function. Yes, don't do that. Okay. Now forget about those wrong things that I just highlighted there. And instead, let's look at a business application. Sometimes both the chain rule and either the product rule or quotient rule are needed. Yes, obviously, we just did that in the previous problem. Very nice. The total revenue from the sale of X stereos is given by this revenue equation. We want to find the marginal revenue equation, which means we have to find R prime, the first derivative of the revenue equation. Let's do that. R prime of X is equal to 4,000. And then here comes the chain rule. We're going to multiply, we'll take the exponent from our original function and we'll multiply it out front. So we could have just written 8,000 right away, but instead I'm going to write it as 4,000 times 2. And then here's that m value, the inner function, 1 minus, I'm going to write it as 1 over 700 times x, close, and then we have to decrease that exponent by 1. So if you'd like to put a 1 here, you can. I would not recommend just, if you want to do that, if you want to put the 1 there, don't just put a 1, because it might look like a derivative mark, and you don't want that, so make sure that it looks like a 1. And then we have to multiply by the derivative of the inner function. So we've got to multiply by the derivative of this stuff. All right, so the derivative of a constant value is 0. So if you'd like to put a 0 in here, you may. And I did this. These two are equivalent to each other. I just chose to write it in a different way. I like writing it as 1 over 700x because that way it looks more like a coefficient. Oh, that was interesting. Oh, as I'm moving and zooming, this is changing shape. Now it's on fire. I'd like to have that 1 over 700 looking like a coefficient because it makes it easier for me when I go to take the derivative of it. So imagine taking the derivative of this. I would take this exponent of 1 and multiply it by 1 over 700, which gives me minus 1 over 700. And then I have to multiply by my variable, but I have to decrease the exponent by 1. So I would get x to the 0. Of course, anything to the 0 power is equal to 1, so you don't have to write that, but if it's helpful to you to write it, then write it. All right, so I think that's the entirety of the chain rule. And this is really the key part of the chain rule. All right, this is the derivative of the inner function. And then let's clean it up. The 4,000 times the 2 makes 8,000. And then this is multiplication by negative 1 over 700. So why don't I write this as 8,000 over negative 700. How about that? And then we'll keep this stuff in parentheses, which says 1 minus, and then if you want to make it say x over 700 again, you can. If you want to leave it as 1/700th of x, that's fine too. And I would say let's go in here and do a little reducing and write our final answer maybe as, let's go negative 80 over 7 times 1 minus x over 700. You know, we could keep going further and further with this to try to clean it up. Let's go one more step. How about negative 80 over 7 plus 80x over 4,900? Right, because I distributed. Here I reduced. Of course, now that I've done that, now I've got to reduce these zeros. So let's reduce one more time, and then we'll be done. That's a heck of a, I don't even know what it was anymore. A marginal revenue equation, yep. All right, throw some x values in there and see what you get. I believe that was the end of this section. It was indeed. That's the chain rule. You could take the chain rule. We probably won't do this in a business calc class, but these chain rules, all of a sudden you get nested trigonometric functions and logarithmic functions, and this stuff can get really dicey. So please make sure that you have the concept down, the general idea of what's supposed to be happening. And by the general idea, I'm unfortunately really talking about this. The idea of taking the derivative of a nested function, a composite function, and I really like the idea of thinking of this as an m value, so that it's that m that's not really changing, right? The derivative of m to the third should be 3 times m squared. Well, you know how to do that. That's easy. But when m is anything other than just an x, then you also have to multiply by the derivative of m. That's the chain rule. All right, go forth and practice and be patient with yourself. And if you have the opportunity to ask questions in class or in office hours, make sure you do that. Be prepared with those questions. Have them maybe even written out in advance so you can ask as soon as you get to class. Thanks for hanging with me on that one. See you next time.